we have seen that derivative is a process. For example, if you had a function for position, the rate of change of position is velocity. So taking the derivative of position function gives us velocity. Taking the derivative of velocity position gives us acceleration. What if we want to do the opposite? Can we find the position if the velocity is given? That opposite process is called antiderivative. Okay, opposite of differentiation, reverse of differentiation. So if we have a function given a function f, so if we can find a function uppercase f such that derivative of that is the function f, we call uppercase f the antiderivative, because it's an antiderivative. So if you do the derivative of that, you get the function back. Okay, so for example, if you have x square function x, okay, so what is the antiderivative of this? Let's look at the function fx equals x squared over 2. Now take the derivative, and fx equals x. Now take the derivative of this, f prime x. What is it? Oh, it is x. So which is equal to fx. So the antiderivative of fx is x squared over 2. Okay, because derivative of that is, so for example, in a table, and there are tables of derivatives, you can see them in appendix. If the derivative, for example, of sine x is cos x, so sine x's derivative in this direction is cos x, then antiderivative, we'll call it as this something called integral sign, opposite direction, the antiderivative of cos x is sine x. This is the reverse process. Derivative of x squared over 2 is x. Its antiderivative of x is x squared over 2. So it's just the reverse arrow. You go from the derivative of a function and say, whose derivative is it? Okay, that's the point. So for example, if I had velocity of a car at all points, velocity is a derivative of position. So what were the positions if I'm giving you all these velocities? So that's called the antiderivative. But since the derivative of a constant is 0, so if you take the function, for example, sine x plus 10, take the derivative of this, it is still cos x. That means the antiderivative of cos x, and we'll show it by a sign like this. So antiderivative of cos x, and we'll show it with integral sign with a dx in front. That's the notation. So the antiderivative of cos x function is not just sine x, but is sine x plus any constant. Because if you take the derivative of the right hand side, what do you get? You get cos x. Okay. So let's find the antiderivative of this, 3x squared. Oh, we know it's x cubed, because derivative of x cubed is 3x squared. What about 1 over x? Oh, natural log x, because derivative of natural log x is 1 over x. So the antiderivative of 1 over x is natural log x. Okay, plus a constant. Don't forget that. So x cubed plus a constant. Natural log plus a constant. Cos x, we already did. It's a sine x plus constant. Ex, antiderivative is ex plus constant. Why? What is the derivative of ex? Is ex constant 0, so it gives you ex. So these can be obtained straight from the tables. If you look at, let's see, appendix A is, so yeah, here's the antiderivative of u to the power n, or x to the power n dx. It will be x n plus 1 over n plus 1. This is antiderivative of 1 over x is natural log x, plus constant is always there. So this is the table of integrals, okay, which are obtained from the table of derivatives. Okay, these are all different integrals. And here the table of derivatives. These are the properties of derivatives. And here, for example, derivative of sine x is cos x. Therefore, integral of cos x is sine x plus constant. Integral of secant square x, or integral means antiderivative. Antiderivative of secant square x is tan x plus constant. Antiderivative. Okay, let's get back to antiderivatives. Okay, they're also called indefinite integrals. I already told you that. So an antiderivative or an indefinite integral of fx dx, or fx, is shown with this sign called the integral sign, fx, with a dx in front. And that will be fx plus some constant. Indefinite integral. For example, the indefinite integral of 2x is x squared plus constant. Why? You can double check. Take the derivative of this. What is it? It's 2x, because derivative of constant is 0. So these functions are all antiderivatives of 2x. It's a family of functions. For any constants, we have infinitely many indefinite integrals. Okay. All right. So straight from, because we know derivatives, if you look at the answer, the antiderivative of that is the original function plus a constant. That is it. So similarly, remember we saw that antiderivative of x was x squared over 2 plus constant. You will see antiderivative of x squared will be x cubed over 3 plus constant. You can check it. Take the derivative of this. It will be x squared. Okay, so in general, antiderivative of x to the n is x to the n plus 1 over n plus 1 plus constant. And you can check directly. The proof is by doing it. So here is the differentiation of a constant. Indefinite integral of a constant is kx plus c. X to the n, derivative is this. Integral of xn is this. Indefinite integral. Natural log x is 1 over x. 1 over x is natural log of x plus c. Okay, and it's given as absolute value because x can be negative here. But natural log x is only for positive x values. Okay, derivative of ex is ex. Integral of ex, or indefinite integral of ex, is back ex plus constant. Sine is cos, so cos is sine. So reverse process. This is the flip of this, the inverse process of this. So all these examples are given. Derivative of sine inverse x is 1 over square root of 1 minus x squared. So the indefinite integral of 1 over square root of 1 minus x squared is sine inverse x plus c. Okay, pretty straightforward. Just look at the table of derivatives and just invert the process. And verification is, if somebody claims that the derivative of this is this, okay, just take the derivative of this to confirm that the answer is correct. So that's verifying. Okay, and just like differentiation was a linear operator, right? The integral or the antiderivative or indefinite integral is also linear. So it's basically integral of fx plus gx is integral of the first plus integral of the second. So you can do each one separately. Whether it's a positive sign, minus sign, and a constant, just go through the constant. Constant comes out of the integral sign. Okay, so therefore, if you have to do integral of these, it is equal to integral of 5 integral of x cubed minus 7 integral of x squared plus 3 integral of and plus 4 integral of dx. So x cubed will be 5x4 over 4 minus 7x cubed over 3 plus 3x squared over 2 plus 4x. This integral of a constant of 1. Derivative of x is 1. Right? Okay. Let me just remove this. Oh. And it is 4x. So here is the answer. So we did it each one separately, because just like differentiation, the integral is antiderivative, or the indefinite integral is also linear. Here, how you can do the second one is divide each one by x. Okay, so rewrite this integral, divide each one by x, x squared by x, and this over this. Okay, this is a typo. So now, taking the integral of these two, okay, this is just x, and this is 4, and this is x, and this is 1/3 of x up there. So 1 minus 1/3 is 2/3. This is integral of, so this one, which is x squared over 2. This one, x to the negative 2 over n. So again, we know that integral of xn is xn plus 1 over n plus 1. So x of negative 2 over 3 plus 1 over negative 2 over 3 plus 1. So n is negative 2 over 3. And you get the answer. Okay, now what about this one? First of all, 4 comes out of the integral. And we know that the derivative of tan inverse x is 1 over 1 plus x squared. So the antiderivative of this, 4 first comes out. And 1 over 1 plus x squared, its antiderivative, we know directly from the table, is tan inverse x plus a constant. Now the antiderivative of tan x cos x, now that's simple because tan x is sin x over cos x, is just sin x. And that is negative cos x, because derivative of cos x is negative sin x, so it becomes sin x plus c. Now we can use this in solving initial value problems. So for example, let's say we know derivative of a function is given. So we find a formula for y by taking the antiderivative of this. So y equals the integral of this, dx, which will be 6 comes out. So it will be integral of x squared dx, which is x cubed over 3. So this becomes 2x cubed plus a constant. So we know that y is given by this. But in the problem, we were given dy over dx equals fx. And let's say y at x0 is given to be y0. Now y is a function of x, right? So we know y equals, so this was given, and let's say initial value of a function y at 1 is given to be 5. These two are given. This is called an initial value problem. It's a differential equation. So y equals 2x cubed plus c. Y is a function of x. Now plug in x equals 1. So y of 1 is 2, 1 cube is just thing, 2 plus c. But that is equal to 5. Therefore c is 3. Now plug it back into the equation. So that means our function is 2x cubed plus c, but c has to be 3. Because initial value, when you plug in x equals 1, we should get 5. This should be satisfied. So the constant that is given to us when we do antiderivative, that becomes useful in solving differential equations when initial value is given. So for example, if we are given speed, oh, here again, a different one, dy over dx is sin x and y0 is 5. Okay, so the y from this, let's integrate this. So y equals integral of sin x dx, which is, so y is negative cos x plus c. Now plug in y of 0. Y of 0 should be 5 equals cos of 0 is 1, negative 1 plus c. So c is 6. So therefore, our answer is 6 minus cos x is the solution to this initial value problem. Now in physics, for example, we could be given that a car is traveling at this speed. Okay, this is the initial speed. When brakes are applied, so deceleration at a constant rate of this. That means the acceleration, so how many seconds elapse before car stops? How far does the car travel during that time? So acceleration is given, which is what? Which is dv over dt. is given, or v prime is negative 15, and v of 0. So it's an initial value problem. So let's take the integral of the differential equation. We get v is negative 15t plus c. Why? Take the derivative of the right side, we get negative 15. Plug in 0. So v of 0 should be c, 88. So this gives us velocity as a function of time. Okay, how long does the car take to stop? That means at what value of t is this equal to 0? Okay, so solve this equation and we get t equals 88 over 15 seconds. Now, how far does the car travel during this time? Okay, now we have a formula for the velocity, but velocity is the derivative of the position function. And initially, let's say we were at 0 position. We have to say how much did we travel during this time. So time is 88 over 15. So now we will solve another differential equation. ds over dt is this. So do the antiderivative of the right hand side. We'll get minus 15t squared over 2 plus 88t plus a constant. This is now our position function. But S0 is 0. So if you plug in 0 and 0 here, then it tells us S0 is equal to c. So c is 0. So this is our function. And we have to find out, see here. But c will be 0, and this is our function. And then we have to find out where is our position at time 88 over 15 seconds. Plug in into this function, and we get the answer.